I received this from student, and this has to do with the homework problem that we have in the live training session. And the question on the surface of it is fairly simple and straightforward. Arguably, you can throw this question under electromagnetics as well, because it is sort of electrodynamics, or you can consider it as part of properties of electrical materials. Back until 2018, they used to have a separate section called engineering sciences, which included these type of topics, right? But now work done by a charge, work done on a charge, arguably it can be part of properties of electrical materials, or it can be part of electrodynamics within electromagnetics. Shouldn't work be equal to, student is using the formula, and then the issue that the student has is with regards to polarity. I'm going to come back to that in a second. So let us look at this problem and try and understand what is going on here. It's a relatively simple, straightforward problem, and you can make a quick sense out of it by sketching it. As I've been mentioning all along, electromagnetics and properties of electrical materials. In fact, even when we go through some of the more abstract topics later on, even in control systems, even in computer systems and software, sketching always helps. So we have two charged parallel plates that are maintaining a potential difference of 2000 volts. Interesting piece of information, a fairly straightforward question. How much work will be required to move two electrons? So this is again a key piece of information. One of the follow-up questions that I've received from students is that, Wasim, two electrons, how do you know that the charge of two electrons is 2 multiplied by minus 1.6 by 10 raised to power minus 19? This is a constant. This is given in the reference handbook, right up front, under units of measurement. So these type of constants, you guys need to be aware of them. We are moving from positive plate to a negative plate. Now this is key. Imagine that this is positive plate, this is negative plate. If you are an electron, and I think this is how I explained in the live training as well. If you are an electron, what would be your tendency? Would you want to stay with the positive plate, or would you want to move towards a negative plate? What do you guys think? Would you be attracted towards the negative plate as an electron, or would you rather stay with the positive? Stay with the positive, right? It's common sense. Now, if this electron, actually there are two electrons over here, so you need to be careful with this. And this is again one of the mistakes that I see students making is that they just carry with one electron, small, minor, silly mistakes, right? But at the end of the day, they all cost points, right? So if they need to be moved to the negative plate, will they voluntarily do work, or will we have to do work on them? An external force will have to do work on them, right? So by sketching this sketch, you are able to essentially jump to the answer in terms of at least whether the work is being done on them or by them without even putting pen to paper in terms of mathematics, right? No formulas, nothing. This is common sense, very fundamental, basic understanding of how electric charge behaves under application of an electric field, which is in this case being generated by two parallel plates, like a capacitor essentially. Now, this is the equation that we are going to be working through, and the student actually sent me a screenshot, right? And the issue that the student is having is, if you look at this, I think he's trying to sketch this out, minus 2q times delta V, right? Minus 2q times delta V. So the student is in agreement with me working through this equation, which is given in the reference handbook, right? What is the Q? It is 2E, right? 2E. Now, this is where things become a little bit tricky, because when you look at the solution, so what he ended up doing over here is that we have a 2 and then we have a minus Q. He absorbed this minus sign as part of the charge of the electron. Are you guys seeing what's happening here? And then for delta V, he just used 2000. It's very wishy-washy. It is very, very wishy-washy. The right approach is how I have shown here. So we have minus, it is going to stay. It is coming from the original formula. Don't mess around with the original formula. How much charge are we moving or is being moved? 2 times electron. So 2 is a scalar quantity. It's just a number. Pull the 2 out. So you end up with minus 2, right? And then charge of electron is minus 1.6 by 10 raised to power minus 19, right? So it becomes minus 2 minus 1.6 by 10 raised to power minus 19 coulombs, right? And then we have an integration from point 1 to point 2, E dot dl. So what is E? E is the electric field, correct? Electric field direction is going to be from the negative plate to the positive plate. dl is basically the incremental distance that we are integrating over that delta, the difference. V dot dl results in delta v. We know this from the reference handbook. So we can just simplify that integration, and you have to be smart about these integrations. And I've explained them systematically in Maxwell equations, especially when you're using the vector form, that sometimes students see integrals and they throw their hands in the air and they're like, I'm not doing integration. This is too difficult. I'm going to skip this question. At the end of the day, integration of electric field over incremental distance between point 1 and point 2 is simply equal to delta V, the change in the voltage or the potential difference. Now, the difference between these two is 2000 volt. From the standpoint of the electrons, when you're moving from the positive plate to the negative plate, what is that delta V, guys? What is that change in potential? Is it an increase in potential for the electron or decrease in potential? Electron is going from a positive plate to negative plate. So positive is high potential or low potential. Imagine you are that electron and you are being made to move from positive plate to negative plate, correct? Right? So you're going from a high potential to a low potential. What is the change? What is that delta V? I did not mention that delta V polarity over here. I didn't. That is something that you have to figure out. And in all fairness, this problem statement, the way it's worded, is still fairly simple, straightforward. There are so many curveballs that I can actually throw in here. So we agreed that we are going from a high to a low. So what is the change when you're going from a high to a low? Is the net change energizing? Is the net change positive or negative, right? If you go from a high mood to a low mood, what is the net change? It's negative, right? So this is minus 2000 volt. See? This is the right way of approaching this problem. What the student is trying to do over here, it's messy. It is asking for trouble, and rightly so. Like he wasn't able to make sense of the polarity at the end of the day. You need to break it down into small pieces, right? You need to know what you're doing. And in order to avoid mistakes, you need to sketch these problems out. So this is how it's going to work out. How many negative signs we have being multiplied? How many negative signs are being multiplied? We have a negative here and we have a negative here. When you multiply three negative signs together, what do you get? A sign or a positive sign at the end? Three negatives multiplied together give you a negative sign. And what did we expect before even jumping into the mathematics and the equations and the calculations? We expected that the work would be negative. We would have to do work, right? Because at the end of the day, we are taking that electron, moving it from a positive plate to a negative plate. So it all comes together. The equations, the formulas, the sketches, the visualization, right? And the actual intuitive sense of how things are working out. But in order to do that, you need to have a sound conceptual theoretical understanding. And that's what we've tried to achieve by going through the theoretical explanations within the on-demand course, quizzes, mini exams, homework assignments, live training discussions. So my response to the student was fairly simple, that, hey, minus E minus Q times E dot V minus remains as it is because it's 2 times minus 1.6 in the solution because of electron charge and so on. It was a little bit more detailed, but this is sort of the summary, and I've broken it down for you guys step by step a moment ago. So the key takeaway, please take some time, at least during your preparation, to sketch things out and visualize them. If you don't do it right now, don't expect that magically all of a sudden you're going to turn into that great artist who can think in 3 dimensions during the exam and take care of these type of problems within 3 minutes. And if you want to learn more about preparation of FE Electrical and Computer exam and the P-Power exam, then check out these playlists over here. Thanks for watching, and I'll see you soon in the next video.